Hello and welcome back. In the last video we looked at cleaning up the code a little bit and adding some tests. And in the video before that we looked at while loops, which means that now it's time to look at for loops. And for loops is a statement, and it's added at the same level as while loops, as you can imagine. So first of all, we definitely want one in here, which we'll call for statement, and it needs a bunch of things. So we want like this kind of structure where we have a variable declaration, a variable test, a variable incrementer. But that doesn't have to be there, as you see here with the question mark, because this could be incremented down in the body of the for loop, so it's actually optional. And then there should be some kind of body of the for loop. So let's call it variable declaration. It needs to be an assignment, right? So maybe we can, like, it has to be this kind of statement. So it means that it has to be a statement, and then there is, let's call it a condition, which has to be an expression that evaluates to a true or false value. Then there is something we can call the incrementer, which is an option of an expression. And actually, it's kind of interesting. So he's saying that this is also optional. Actually, I read it wrong before. So the first one is a variable declaration or an expression statement. And the next one is an expression, which would be that one, and then which is optional, and then this one is also optional. So, but it actually means that we should probably model this as an optional. Then let's do this for lack of a better idea. We can make it a box of a statement, so it should point to this guy, or we can make it just an expression. But I think we'll just keep it like this for now. The condition is also optional, and the incrementer is optional. Maybe this is more symmetric, like the first element in the for loop thing is a statement and the rest is an expression. So when we have that, then we need the body, which is just as another statement. And let's format that. So now he's suggesting that to handle for loops, of course we could implement it just like we did with any of the other statements. But the author of the book wants to consider it as like syntactic sugar, which means that, you know, if you have a for loop like this, you can turn it into an equivalent while loop, which would look like this. And if you do it like that, then this is essentially syntactic sugar, meaning it's just something you write as a shorthand for another construct, namely, now I lost it again, this one. So we are gonna, the advantage of that is that you don't need to optimize like two different language constructs, for example, but whatever the case is, we're gonna try this, so we also get like familiar with desugaring. And of course, it's gonna be a little bit different than the way he does it in Java. So it probably means that we don't need this, or we don't want this. Right, instead we, unlike the previous statements, we won't add a new syntax tree node, instead we go straight to parsing. So basically in the parser, if it sees a for loop, it should turn it into equivalent while loop statement. So let's zoom out again. I hope it's not too small. Okay, so if we see a for loop, we do something and use the same pattern. Here's where it gets interesting. The desugaring is going to happen here, so we'll build this method one piece at a time, starting with the opening parentheses before the clauses. So, as always, we try to eat a left parenthesis. Then we try to get the initializer. What do we say here? For now, without knowing the full context, let's put it to none. Self.match. I forgot this. Self.match token. It's a variable declaration. Then the initializer is sum. Well, let's get the declaration first. Else we'll get some expression. Statement. Let's check that I didn't get any types wrong here. Now we get some warnings, which is okay, because this function is unfinished. So that's fine. Let me just check. Okay. So now we need to get the condition. And we will say, we also have this check, right? So if not, self check, semicolon. Then condition, do the same kind of trick. And we want this to be an expression rather than a statement, so we'll just call the expression function. and otherwise it will be none. And then we have to consume a semicolon. So what have we done? We've basically, like, this is done. How do I write that? I write it like this. Check mark. And then we're looking for this. Then something here. Semicolon, something, something. So first we get the left parenthesis, then we get the initializer, which is the first something. Then something, let me check this check function, what it does. Yeah, just the peaks. So it's kind of funny that if we don't find a semicolon, okay, so now I see the point is because this variable declaration will already consume a semicolon and the expression statement as well. So all of this block, that's right here, it consumes something plus the semicolon. And now here, if we don't see a semicolon right away, so it could look like this, then we will see two semicolons. But if we don't see that, we need an expression. So we'll say consumes something, semicolon. And the expression does not consume a semicolon, apparently. Yeah, the expression doesn't. And that's why we need to explicitly consume it here. Great, again we look for a semicolon to see if the clause has been omitted. The last clause is the increment. Again, we see if thing is empty, and we need to try to get the expression. And then we need to consume a right parenthesis. So now we've got everything except the body. So let's get the body. We've passed all of the various pieces of the for loop. The resulting st nodes are. I'm not sure why he says return body. It's a bit weird. This, okay, so we've passed all the various pieces of the for loop. This is where the desugaring comes in. We take those and use them to synthesize syntax tree nodes that express the semantics of the for loop like the handy sugar example I showed you later. The code is a little simpler if we work backwards. So we start with the increment clause. Okay, so as you can see here, he's modifying the body. So let's do that. So we'll say if let sum inc equal increment. Then we will change the body to be a block statement, and let me remind myself how it's just a list of statements. Actually, it's yes, a list of blocks of statements. So let's do that. So we need a vector and then a box new of the old body and a box new of an expression statement on the increment, or rather that one. Let's format that. No, there's some kind of mistake. Like that. Then we need to say statements. Yeah. Check it. All right, and this one has to also be named. And now we get the warnings of the unused variables, which is fine because we're going to use them right now. And the increment, if there is one, executes after the body, exactly what we've done. We do that by replacing the body with a little block that contains the original body, followed by an expression statement that values the increment. Now we will do the same for the condition. If it is a sum, then we will do something. So actually, let's say match condition with none. If it's none, then we will say the condition is just literal. Is it really called literal? Yes, literal with otherwise it's that. And then in here we will say the body is now a while statement where the condition is this one and the body is the old body. Format that, check it. And this has to be while statement. And just some warnings again. Now we check the condition and the body and build the loop using primitive while loop. If the condition is omitted, we jam in true to make an infinite loop. Yes. Yeah, so if there's no condition, it's implicitly true. Otherwise, it is a condition that we need to evaluate. If the condition is omitted, yeah. And finally, we look at the initializer. if it has a value, then we make a new block statement, which has a list of statements, the first of which is the initializer, the second of which is the old body. And we have to remember to use the unpacked value. Right. 152, it's never read, that's fine. And that should be it. We can kind of read backwards now and see what happens. So the body, it will first run an initializer if there is one. And then it will run the old body. The old body is up here. It's a while loop. So it will first, while loop with some condition and a body, where the old body is defined up here. It is another old body, and then it's the incrementer expression. And finally, the old body is just a statement. So it unwraps to, or desugars exactly to this thing. Right? Initializer here, body, which is then the while loop. Here we get a while loop, condition, so on and so forth. That's great. So then we're done, and we can say return body or just body. And it has to be an OK. And now let's add a test. Finally, let's finish reading first. Finally, if there's an initializer, let's run. Yes. That's it. Our interpreter now supports C-style follows. We didn't have to touch the interpreter class at all. Since we desugared to nodes, the interpreter already knows how to visit. There's no more work to do. It's powerful enough to entertain us, at least for a few minutes. Let's make a test for this. Test out of this. Two and two. Now, to actually write the test, we need to we could just like calculate the Fibonacci numbers ourselves, which is like a little bit easier. So let's make an empty vector, and then for I in 0 to 21, let's say A equals 1, B equals 1, and how do we want to do this? We do need the temp as well, I think. So B has to be equal to A plus B, and A has to be equal to B, but not this B. It has to be equal to the old B. So we'll do that. And this shouldn't be let, actually. It should just be assignments. And then we will push A. So I think that should do it. So We need a line for each Fibonacci number. And we check on all of those. That's the line there is equal to this one to string. Let's see if we can get that to run. We cannot. And it's because we need to rename this. Value temp is never read. What are you talking about? Am I not reading from it here? This one we don't need. Ah, and here we can do that. That's what it meant. And of course it failed. That is weird. Let's try to run the for loop. Which is, as far as I can see, correct. But it's starting at 0. So let's do that. Push the A here. Check it. And it's failing. It's failing here, which is interesting. And we have to do that. Huh. This is not, this is, it's still in that. Okay, it's because there's an empty line or something. Okay, now it passes. So all of the values are correct. I think that's pretty cool. So now we have like kind of a real language. And we can also do things like implement game of life or other things like that. But probably that's something for another video. Let's see, a few chapters from now, when Looker supports first class functions and dynamic dispatch, we technically won't need branching statements. We never do this. Okay, so that's it for this time. Thank you for watching.